What is a process? In computing, a process is the instance of a computer program that is being executed by one or many threads. There are many different process models, some of which are lightweight, but almost all processes, even entire virtual machines, are rooted in an operating system process which comprises the program code. Assigned system resources, physical and logical access permissions, and data structures to initiate, control, and coordinate execution activity. Depending on the OS, a process may be made up of multiple threads of execution that execute instructions concurrently. While a computer program is a passive collection of instructions, typically stored in a file on disk, a process is the execution of those instructions after being loaded from the disk into memory. Several processes may be associated with the same program. For example, opening up several instances of the same program often results in more than one process being executed. Multitasking is a method to allow multiple processes to share processors and other system resources. Each CPU core executes a single task at a time. However, multitasking allows each processor to switch between tasks that are being executed without having to wait for each task to finish. Preemption is what this is called. Depending on the operating system implementation, switches could be performed when tasks initiate and wait for completion of input-output operations, when a task voluntarily yields the CPU on hardware interrupts, and when the operating scheduler decides that a process has expired its fair share of CPU time, for example, by the completely fair scheduler of the Linux kernel. What a funny name. Well, a common form of multitasking is provided by CPUs. Time sharing. A common form of multitasking is provided by CPUs. Time sharing. That is a method for interleaving the execution of users' processes and threads, and even of independent kernel tasks, although the latter feature is feasible only in preemptive kernels such as Linux. Preemption has an important side effect for interactive processes that are given higher priority with respect to CPU-bound processes. Therefore, users are immediately assigned computing resources at the simple pressing of a key or when moving a mouse. Furthermore, applications like video and music reproduction are given some kind of real-time priority, preempting any other lower priority processes. In time-sharing systems, context switches are performed rapidly, which makes it seem like multiple processes are being executed simultaneously on the same processor. This simultaneous execution of multiple processes is called concurrency. For security and reliability, most modern operating systems prevent direct communication between independent processes, providing strictly mediated and controlled inter-process communication functionality. Yikes, what a heavy last sentence that is. And so, let me go ahead and show you some pictures. For some reason, this does not copy very well to the Word document. But here it says program versus process versus thread. And it says scheduling, preemption, context switching. So if we go over here, here's a program, and here are instructions. This is the disk, so programs can exist on disk in storage there. Now when you instantiate, looks like the program is the process now. Over here, the arrow is labeled abstraction, and we see process 1, process 2, so on. These processes exist in RAM. They lead us this way by saying collect pointers, table of thread pointers and their priorities. So here we have something called the scheduler, and it's able to context switch between threads, figuring out which one should go next to right here it says execute. Here's a list of processes as displayed by htop. Each process has an ID that belongs to a user. And here's a variety of other columns. You can look at the memory section to see how much of the RAM is being used by these processes. Let's look at a process table as displayed by KDE system card. Not much to say here. This process takes 2% of CPU utilization. Over here is how much memory it takes, how much shared memory, and then this looks like a file path under total memory. I don't have any experience with KDE system guard. Okay, so that's all the pictures worth looking at. Let's finish the article. It says representation. In general, a computer system process consists of, or is said to own, the following resources: an image of the executable machine code associated with a program, memory, typically some region of virtual memory, which includes the executable code, process-specific data, that is input-output, a call stack to keep track of active subroutines and or other events, and a heap to hold intermediate computation data generated during runtime. Operating system descriptors of resources that are allocated to the process, such as file descriptors, this is a Unix terminology term, or handles, which is more of a Windows term. There is also data sources and sinks. Next up is security attributes, such as the process owner and the process's set of permissions, that is to say, allowable operations. The processor state, such as the content of registers in physical memory, addressing. The state is typically stored in computer registers when the process is executing and in memory otherwise. The operating system holds most of this information about active processes in data structures called process control blocks. Any subset of the resources, typically at least the processor state, may be associated with each of the process's threads in operating systems that support threads or child processes. The operating system keeps its processes separate and allocates the resources they need so that they are less likely to interfere with each other and cause system failures, for example, deadlock or thrashing. The operating system may also provide mechanisms for inter-process communication to enable processes to interact in safe and predictable ways. Now, a multitasking operating system may just switch between processes to give the appearance of many processes executing simultaneously, that is, in parallel, though in fact only one process can be executing at any one time on a single CPU. Unless the CPU has multiple cores, then multi-threading or other similar technologies can be used. It is usual to associate a single process with a main program and child processes with any spin-off. Parallel processes, which behave like asynchronous subroutines. A process is said to own resources of which an image of its program in memory is one such resource. However, in multiprocessing systems, many processes may run off of or share the same reentrant program. So a quick side note, in computing, a computer program or subroutine is called reentrant if multiple invocations can safely run concurrently on multiple processors. So many processes can run off the same reentrant program at the same location in memory, but each process is said to own its own image of the program. Processes are often called tasks in embedded operating systems. The sense of process or task is something that takes up time, as opposed to memory, which is something that takes up space. If a process requests something for which it must wait, it will be blocked. When the process is in the blocked state, it is eligible for swapping to disk, but this is transparent in a virtual memory system where regions of a process's memory may be really on disk and not in main memory at any time. Note that even portions of active processes or tasks executing programs, that is, are eligible for swapping to disk. If the portions have not been used recently, not all parts of an executing program and its data have to be in physical memory for the associated process to be active. An operating system kernel that allows multitasking needs processes to have certain states. Names for these states are not standardized, but they have similar functionality. First, the process is created by being loaded from a secondary storage device, such as hard disk, CD-ROM, whatever, into main memory. After that, the process scheduler assigns it the waiting state. While the process is waiting, it waits for the scheduler to do a so-called context switch. The context switch loads the process into the processor and changes the state to running while the previously running process is stored in a waiting state. If a process in the running state needs to wait for a resource, like wait for a user input or file to open, for example, it is assigned the blocked state. The process state is changed back to waiting when the process no longer needs to wait. Once a process finishes execution or is terminated by the operating system, it is no longer needed. The process is removed or just instantly. When removed, it just waits to be removed from main memory. Now, this next part is really interesting. The section is titled Inter-Process Communication. When processes need to communicate with each other, they must share parts of their address space or use other forms of inter-process communication, IPC. For instance, in a shell pipeline, the output of the first process needs to pass to the second one, and so on. Another example is a task that can be decomposed into cooperating but partially independent processes, which can run at once, i.e. using concurrency or true parallelism. The latter model is a particular case of concurrent execution and is feasible whenever enough CPU cores are available for all the processes that are ready to run. Now, it is even possible for two or more processes to be running on different machines that can run different operating systems. Therefore, some mechanisms for communication and synchronization, called communications protocols for distributed computing, are needed. And the example is the message passing interface, often simply called MPI. Now, I always love computer history. That section says by the early 1960s, computer control software had evolved from monitor control software. For example, IBSys, maybe they pronounce it. But it had evolved from this monitor control software to executive control software. Over time, computers got faster, while computer time was still neither cheap nor fully utilized. Such an environment made multi-programming possible and necessary. Multi-programming means that several programs run concurrently. At first, more than one program ran on a single processor as a result of underlining uniprocessor computer architecture, and they share scarce and limited hardware resources. Consequently, the concurrency was of a serial nature. On later systems with multiple processors, multiple programs may run concurrently in parallel. Programs consist of sequences of instructions for processors. A single processor can run only one instruction at a time. It is impossible to run more programs at the same time. All right, and that's all the interesting parts of the history, and that will bring us to the end of the article.